Chapter 6 is all about confidence intervals, and we start off in 6.1 talking about confidence intervals for the mean of a population, and it says right here that the population standard deviation is known. So what we're working with here is trying to make an estimate for an unknown population mean. So for example, we don't know the weight of all the whales in the ocean, and there's no way to catch them all and actually weigh them. That would be impossible and impractical. But we can capture a sample of them, weigh a sample of whales, and our first way to estimate what the population average weight would be is to use a point estimate. And that's a pretty simple idea. It's we get our sample, we figure out what the average weight of our sample of whales is, and that's our estimate for what the population weight would be. So a point estimate is just a single value. You're finding the mean from your sample, and that's your estimate for the mean of the population. Going through example 1 in the book, it's on page 298. Someone's trying to find the mean number of hours worked for all the grocery store employees in a county. And rather than try to get a hold of every single grocery employee, we're just going to look at a sample of 40 employees. And here's how many hours the 40 people in the sample worked. And so we can find the mean, the average of those 40 people. And we do right here. X bar, the mean of our sample, is 29.6. And so that would be our point estimate for what the mean is for the actual population of all grocery store employees. Now, the chances that our point estimate is exactly right is virtually 0% chance. Depending on what sample you take, every single sample is going to have a different mean. So you're going to get a different point estimate for every single sample. And the chances that it's the exact right number that matches up with the population mean, virtually 0%. So rather than just get a single number and use a point estimate, we often like to make an interval estimate. And that's where the whole idea of confidence intervals is going to come in. So we always start off by finding our point estimate. So for example, our grocery store employees, we guessed that the population mean would be 29.6. We are using our point estimate from our sample. But then we're going to create an interval on either side. So we'll go a little bit less than 29.6 and we'll go a little bit more than 29.6. And we're going to be very confident that the real population mean is somewhere within this interval. And we're going to discuss in these future videos exactly how confident we are and exactly how wide we want to make this interval. But we always are going to start with our sample mean in the middle of our interval. That's our point estimate. It's probably not right, virtually 0% chance that it's exactly right, but we're going to be really confident that somewhere within this interval we build, the real population mean is somewhere within that interval. Every time we build a confidence interval, we're going to associate it with a level of confidence. And so I'll just pick one here. Let's say we have a 90% level of confidence. What that means is that if we use our methods here of getting our sample and building our confidence interval, we know that 90 out of 100 times, 90% of the time, the interval that we build is going to contain the true population mean. Now, if our level of confidence was 95%, it would mean that using our techniques to build the confidence interval, 95 out of 100 times, we know that our interval contains the true population mean. So to determine what level of confidence you're going to use, that's really up to the person who is running the experiment and creating the confidence interval. Most of your problems will tell you which one to use, but in real life practice, someone just has to pick. And the drawbacks of picking a lower confidence interval is obviously that you have less confidence. The pro of that is that your interval will be smaller, and then as you increase your level of confidence, you have to get a wider and wider interval. And to think about that, that should make sense. If this was our guess for where the real population mean falls, and we have an interval here, the wider we make it, the more numbers we're including, the better our chances are of actually containing the real population mean. So the wider we make this interval, the more confident we become. And sometimes you don't want a really wide interval. So that's the drawback of being like 99% confident. A really wide interval doesn't give you as precise information. For example, if our interval was all the way from 20 all the way up to 40, and we said the mean, we are 99.9% confident that the mean number of hours worked by a grocery store employee is between 20 and 40 hours, that hardly tells you anything. That's such a wide range. So being really confident isn't useful if the range is too wide. And conversely, getting a really small range isn't very helpful if your confidence level drops too low, because then you can't really put any trust in your range. So it's all about finding that balance, and it'll really depend from situation to situation what level of confidence you would want. And as we construct these intervals, the key underlying thing that's going to make it all work is the central limit theorem, and that we know that the sampling distribution of the sample means has a normal distribution. So we're going to be able to use the probabilities from our normal distribution in order to create intervals that have the confidence we want. And the way the normal distribution is going to come into effect is when we calculate our margin of error, which we abbreviate with E, and that's basically how wide our confidence interval is going to be, how wide we need to make it. And here's the formula. It's the z-score based on your level of confidence. That's what z with the tiny c means. Our formula is the z-score based on the level of confidence multiplied by the standard deviation of our sampling distribution of our means. And we can figure this out. Remember, we learned the formula for that back in chapter 5. It's the population standard deviation divided by the square root of your sample size. So we're going to take that and multiply it by the z-score based on the level of confidence that we want. And once we have our margin of error E, that's how we know how wide to create our confidence interval. We start from our sample mean and we subtract that margin of error to get the lower bound, and then start from our sample mean and add that margin of error to get the upper bound. And to look back at that original example we did, that's what happened here behind the scenes. We start with our sample mean, and this is the margin of error. So the difference between 27.5 and 29.6, which looks like it's 2.1. So you subtract 2.1, you get your lower bound of your confidence interval, and then you add 2.1 and you get the upper bound of your confidence interval. And so to wrap up this video, I want to talk through a few things about the normal distribution to make sure everything's clear. The first thing is just to recall from chapter 5 that our sampling distribution of the sample means, it is normal, and the mean is equal to the population mean. So that's crucial to remember. The population mean is equal to the mean of our sampling distribution. So right here in the middle of the distribution. And this picture has colored in blue 90% of the distribution. So there's a cutoff side to the right that it's saying is 1.645, and there's a cutoff side to the left that it's saying is negative 1.645. And that in between those critical values, 90% of the data lies. Or another way to think of that, 90% of samples we get, 90% of them, the mean of those samples is going to be in the blue area. Now, how do we get these numbers, the 1.645? Well, if we want 90% to be within our cutoff, that means 10% is outside. So 1 minus 90%, 1 minus our confidence level gives us 10%. Well, there's two sides, so that means 5% here and 5% here. So half of our 10% gives us 5% in each of the tails. And to pull over my Excel, remember learning this formula, norm.s.inverse 0.05. So if I want to know how to get 5% in the tail, I type in 5% into this formula, and it gives me back the critical value associated with 5%. Now, Excel only told you the negative critical value, but by symmetry, you know the positive critical value is exactly the same numbers, just positive. So recall the formula for finding any z-score, any critical value. The z-score, you take the data value minus the mean divided by the standard deviation. So what happens if you multiply both sides by the standard deviation? You would have this. And what it's equal to is the data value minus the mean. Think about what that is. That's distance. The data value minus the mean tells you how far this distance is. When you subtract two values, you can get the difference between them, or the distance. Now, does this look familiar? The z-score multiplied by the standard deviation. That's the exact definition for what our margin of error is going to be. So our margin of error, again, is the distance from our cutoff points here to the mean in the middle, which, again, reminder, is our population mean. So when we find that margin of error, we're finding the distance from the population mean, which we know is in the middle of our distribution, to our cutoff lines, where if these are cutoff lines for 90% confidence, it would be the distance from the population mean to where the cutoff line for 90% of the data is. So 90% of the data is in the blue. And so look at what this would look like. 90% of the time when we get a sample, the sample mean will be somewhere in this blue. And let's say it's right here. We get a sample mean, or we draw a sample and the sample mean is right there. Well, then we would use our margin of error to construct a confidence interval. We'd take our sample mean, subtract it to get the lower end of our confidence interval, and we take the sample mean and add it to get the upper side of our confidence interval. So from down here all the way up to here would be our confidence interval. And you can see that the population mean is within the confidence interval. It's over here. So if we draw a different sample, we're going to get a different sample mean if it's really close to the population mean. Well, then when we use our margin of error to draw and get our lower bound and our upper bound for our confidence interval, again, our population mean is right within our confidence interval. It's actually really close to the middle because our sample mean was really close to the population mean. And this will happen no matter where you draw within the 90% area. So a different sample could give us a sample mean further off to the right. But again, when we use our margin of error to get the lower bound and the upper bound of our confidence interval, again, the population mean is within that interval. So the only time we're going to not have the population mean in our interval is when we get a sample that has a sample mean out in one of the tails. So either in this 5% tail or this 5% tail. So if we get a sample mean down there, we would construct our confidence interval, and we'd still say we're 90% confident that the population mean lies within this interval. But we'd be wrong this time, which will happen. 90% confident, 10% of the time you're not going to be right. Our population mean is outside of the interval.